Good morning. So we have a handful of exciting science talks, but before we do that, I think Marion and Julia want to give an update on what happened the other night with the Early Career Researcher Workshop.
Yes.
Yeah, thank you.
Can I pull up the slides?
Yes, sorry.
Okay. It's all good. They should be in the same folder. Yeah, perfect.
Oh, that's not. Oh, yeah, there we go.
Okay, thanks, Ben. Hi, everyone. So again, I'm Marion McKenzie. I'm a postdoc at Colorado School of Mines.
Hi, everyone. I'm Julia Andreasen, a PhD student at University of Minnesota.
And on Tuesday night, we got all of the early career folks together to chat about needs and just where we're at within the WAIS community.
So this is our third annual WAIS ECR workshop. This year was a little spur of the moment, but we have actually been doing it in past years. And essentially what it entails is inviting all the ECRs to an hour-long moment of connecting and communicating. And this was initially brought on by Marion at Paseco. And so we've just sort of continued the same format, asking students to answer certain questions and talk about broad questions related to community, and specifically asking them what a supportive community looks like. So yeah, we broke out into these groups, and then these were some of the examples.
And I'll also add, for members new to the community, Paseco stands for Polar Science Early Career Community Office, and they have a lot of resources, so go ahead and check them out. But we split into groups, and using these 5 guiding questions, we had the groups answer them in 5-minute increments based on their career stage. So we're going to step through each of these questions, but we just wanted to throw this up here so you can see the representation of career stages that were here. Blue was PhD students, yellow was master's students, green was postdocs, and the purple was undergraduate students.
So our first question was, what do you like about the WAIS Workshop community? So now's a moment to pat yourselves on the back for all the great things that they had to say. So the variety and diversity of knowledge and the flavors of science, the size, having it smaller than EDU really lends to more opportunities for connections and networking, especially for those super early career researchers who are looking for potential mentors and advisors. It's easy to attend all of the talks because there's not an overwhelming amount, and it attracts a really wide range of ECR, mid-career, and senior scientists. And then we have a lot of breaks, which is great for networking, again, and chatting, as well as a lot of time for panel discussions. People have liked the venues. This venue is a little different from past years, but I think it's also been favorable. And then archiving all of the science online and recording it has been really great for using it as future academic material. And then ECR funding opportunities. ECRs love money, so that's great. Let's keep that up.
We also asked early career scientists what gaps they think exist in support for technology in the WAIS and general cryosphere community. There was an interest in developing a Jupyter book that would be maintained by the community to describe, access, and use common resources to see up-to-date opportunities. There was a comment that cryosphere courses are not available at many universities, so workshops and shared learning spaces would be helpful for new grad and undergraduate students. Some people were commenting that the venue isn't always super easy to access. Testing equipment and having captions for presentations would make this work more accessible. And the bold statements that are in this slide and a future slide are related to the 2023 WAIS Community and Science Plan that came out. So I just wanted to share the overlap between the two so that we can recognize that the community at large is aware of these concerns and aware of these asks, and so they are being accounted for, but one that was already on the WAIS community plan from last year was that seminal field experience is competitive, rare, and expensive.
So in terms of gaps in support for networking and career development in the WAIS community, there's more interest in group activities or topic breakouts for people with shared interests. So I think that's sort of a natural thing that happens during breakout times, but really enforcing it to create collaboration across labs I think would be really great. For the agenda to go out prior with attendee list with names, specialization, contact info, and a glossary of acronyms. So this is mostly just for folks who don't know anyone coming into this or don't really know all of the terms that'll be used in presentations. This is a great opportunity for give people that extra information. This has been sort of a topic and a debate. I think in past years there's been arguments that there's too many ECRs, not enough ECRs, too many mid to late, not enough mid to late. So some people have really been satisfied with that, others not so much. So that's something I think we can always just continue to evolve, and I think everyone's presence is really valued. And then there's a gap in career discussions for outside of academia, and I think that's something that other groups have talked about. So if you're familiar with the ICE Corps community, there's a group called ICE Crew, which is for ICE Corps early career researchers, which is not just for people who do ICE Corps research, but they've had sessions about careers that are outside of academia. So there's a lot of resources that we can tap into, I think, and bring here as well. And then some folks wanted an announcement for ECR funding a little earlier. Okay, so then, also, what networking and community building resources are you looking to get out of the WAIS workshop? So I think a lot of these points were hit by folks while they were here, but just to reiterate what people are looking for, potential advisors is huge. Gaining a sense of the priorities of the community is really big. Something that we could start to implement is staggering poster sessions. So if you're in a poster session and you want to have time to go see other poster sessions, maybe creating 2 different groups so that you can have that time would be helpful. Starting collaboration, so to get letters of recommendation from mid to late career faculty. Workshop days, so grant writing and new faculty panels, et cetera, that would extend our time at the WAIS workshop, but I think could be a really valuable maybe afternoon activity or Thursday evening activity, Thursday afternoon. And then sort of part of that would be also how to start large-scale collaborations and observe how it happens and what efforts exist. So all of these are sort of just workshop-y types, because another one would be a how-to guide from current or new faculty for setting up everything in your first faculty job. And then lastly, just learning how to formally have a voice and get heard and paid for involvement in setting up the IPY and decadal survey priorities.
So we also asked about what the community thinks should be science and community priorities leading up to the International Polar Year. The first one was defining International Polar Year and just understanding why this is a thing that we're building up to and what it means for the community. But throughout this, we can see that there was a lot of overlap between what ECRs found important and what was in the community and science plan from last year. So I won't spend too much time on this slide. But we can write this up more formally so it's available to the community as well.
So these were some goals that the 2023 cohort sort of came up with, and our checkpoint is a little off, but we did do one of those things this year, which was really exciting. We did the 1-minute introductory slide for people without posters or talks, which again, I think is just great for exposure for those that are not necessarily involved. And the rest of these, I think, can be like more of a long-term goal and exercise for us to keep in mind, and things for future WAIS workshop organizers to maybe incorporate. But yeah, I think we're doing all right.
So for this year's goals, we adapted a lot of the previous year's thoughts where we have present cryo groups and organizations, use fewer acronyms and include a glossary of terms in the meeting agenda, consider pre-WAIS entry-level workshops for early career scientists, organize a cross-career staged icebreaker activity at the start of the workshop, formalize a mentorship program between mid and early career attendees, and include closed closed captioning for slides, and the second part I saw us doing, but maybe making it more clear that this is available to the community, is to allow presenters to view their slides before presenting. So thank you so much for listening to our report out. Here are a few resources on this slide.
Yeah, and we look forward to doing this, I think, in future years, just having the ECRs get a moment to connect and voice out their opinions. And if you have any questions, feel free to reach out to us. Or if you're interested in getting involved in organizing something like this next year, let us know. Thank you.
Maybe one quick question while we're swapping. We'll bring you guys up on the panel too, so if there's more questions then yeah. All right, now we have 4 great science talks. This session is on observations and modeling. So the first talk is from Paul Winberry, and he's going to share with us some seismic observations from Thwaites Glacier.
All right, thanks everyone. And I'm here on behalf of quite a large team that was part of the International Thwaites Glacier Collaboration, the first acronym, since we just heard about acronyms. And we were called the GHOST team, which is a really awful acronym that Sridhar doesn't particularly care for us. But anyway, we're geophysicists. And I'm going to talk about some of our initial results. So we got delayed like a lot of teams, and so this is still pretty early work. But it's basically, this is what this entire project is about, is trying to understand the subglacial environment and how that influences ice flow. All right. And so we're going to go to Thwaites Glacier. This is from the NASA Measures project. This is the flow speed of Thwaites Glacier. So the sort of reddish colors are, where the ice is moving quite fast. I think we've seen this a few times, where ice is, going from right to left. And this is, a major area of concern for those of us who want to understand the future of the Western sheet. But if you invert that, and figure out the basal friction at the bed of the ice sheet, you get something that looks like this. Now the color scales are basically blue is where the bed's really weak, and the sort of darker reddish to white colors are where the bed is much stronger. And it really is this variability in basal drag that controls how fast the ice sheet is flowing, and how you describe that in space and in time is going to influence the future evolution of the ice sheet. But one of the things I like to think about is if we can't understand why we have these red and blue spots on this map, can we really predict what's going to happen in the future? What is the physics, what are the physical processes controlling the colors on this map? And I don't have the answer to that, and I won't get to it. But I think this is something we still need to think about as a community. And that was the entire goal of the GHOST project. And we have ice sheet modelers, not just geophysicists. Okay, and so, one of our study areas was focused sort of as close as we could get to the grounding zone safely and deploy instruments. And so we're going to zoom in on that black box there in the middle, which is, 50 kilometers by 50 kilometers or so. Okay, and so now we've zoomed in. We still have that basal drag map. So again, like red are regions of high basal drag, high friction, and the blue spots are regions of relatively low basal drag. And so we want to understand the physical controls across these boundaries. And one of the experiments we did a lot of experiments. We drug radars, like we did active source seismic, we did some magnetotellurics, we did some gravity work. And so I'm just going to focus on this part of our subset of our experiment, where we put all these little white dots are places where over 2 field seasons we put out 3-component high-frequency seismometers. And the primary goal of this was to study natural source seismicity coming for the bed, so we can learn about physical properties. But what's interesting about this array is that it spans a region from red, high basal drag on the top area of the screen, down to a sort of lower basal drag on the lower part of the screen. And it doesn't go farther downstream because there's a lot of crevasses. And so we want to know, is there this fundamental change? And as I said, Amanda Willett at Penn State and Jaden Zach at the University of Madison, Wisconsin are doing like the real some of the most interesting work on this is there's tons and tons of ice quake coming from the bed that are going to allow us to map in a different way variations in physical conditions at the bed. Okay, so what's noteworthy about this, if you're not a seismologist or a geophysicist, is this is over, this is close to 200 white dots. These are seismometers, and so previous experiments that were focused on glacial geophysics and glacial seismology would have order 10 instruments. So this is really a game changer, and this is a technological advance. So we're still learning how to really exploit these data efficiently. And time had similar large arrays of passive seismometers on the shear margin. So I think there's going to be a lot of really exciting stuff coming out of glacial seismology world at this meeting in the next few years. Okay, so is there a fundamental change? One thing I want to address in this talk is there a fundamental change in sediment thickness across this boundary? And why do we think that might be interesting? Well, one of the most I think, best examples is if we go to the Saipo Coast and we look at some of the onset regions of the ice streams there. And so you'll see a really strong control between fast flow and sediment availability. And this is from Leo Peters' work, but basically what we're looking at now is a 35-kilometer long cross-section across an ice stream. Ice is flowing out the board towards you. And the black dots there are the ice flow speed. So you can see you're going across an ice stream. In the middle of the figure, the ice is moving, about 80 meters a year. And towards the outside edge of the figure, the ice is essentially stagnant. And what you see in the hatchet and colors there in gray is where we have sediments. We have a sedimentary basin. We have hundreds of meters of sediments that perfectly define the boundary between the ice stream and the stagnant ice. And so we know from other places that sediment availability can be a strong control on fast glacier motion. So that's why we're interested in looking across this transition. And how are we going to do that? Like I said, one of the ways we typically do that is with active source geophysics, especially explosive source seismic work. And we did some of that, and there's some great work coming out of Temple, is going to come out soon, discussing, not in this area, but other parts of Thwaites. So how are we going to do this with passive seismometers? So in geophysics and the cryosphere, we often do a lot of active source geophysics, whether it's radar or seismic work, where we send a pulse down into the ground and record something back. But another way you can use seismic data, passive seismic data, instead of using sort of an artificial source, we can actually use earthquakes that are from hundreds, thousands of kilometers away, and we can use them just like an explosion. Basically, they travel through the earth, and they bounce around, and we can learn something about the subglacial structure. All right. And this is a suboptimal. It's a kind of a blunt tool. We have very low frequency content, so we're not going to be able to image, meter scale sedimentary deposits, but we can get a sort of a large scale imaging of where there are hundreds of meters of sediments or not. So it's a suboptimal tool, but it's what we've got, and it's another thing that we can use to tackle the problem. Okay, so just really quickly, this is going to be like a 30-second overview of seismology, earthquake seismology. If you, we're going to do something called receiver functions, which isn't important. Basically, we're recording seismograms from earthquakes. And if you had your seismometer, the black dot up there, and you put it on a rock in Antarctica, and you record an earthquake from far away, and you'll get a seismogram. This is like a 7-second synthetic seismogram over on the right. So basically, the spike is the amplitude. That's the first energy to arrive from your earthquake. Basically, that's all you'll see in the first few seconds. It's pretty boring. But what happens is if you put ice on top of your bedrock, which we have a lot in Antarctica, there's your seismogram now on the right again. But now we have all these wiggles bouncing around. And what those are basically the seismic energy coming from your earthquake gets trapped in the ice and bounces around. And if you wanted to, you could figure out how thick the ice was from that, but we have better ways to do that. But what we can't do with, say, radar particularly well is if there's something under the ice. But what happens if we put some sediment beneath the ice between the bedrock? Basically, sediment also has a very different acoustic impedance than bedrock. So basically now, the energy can also get trapped around in this ice sediment layer. And so then we can use these reverberations to get at, basically, is there sediment or not under the ice? And so this is an example. Let's see, we've got like 2 minutes to go. And so just to show that we can do this, and so the red line in the top panel here is our observed seismogram from Thwaites Glacier at one location, and basically the black is a best fit synthetic. The blue line is what it would look like if it was just ice on bedrock. So it doesn't even if you're not a seismologist, I think you can see the blue wiggle doesn't look like a lot like the red wiggle, and the black wiggle looks a lot closer to the red wiggle, right? And that's geophysics. And there's some trade-off. And anyway, so there's some trade-off between, and so on the bottom, basically, we search over a grid space, basically, just sediment thickness versus VPS-VS ratio, which tells us something about the material properties, basically how much water there is in the sediment. And we can try and do this over the entire array. And so now we've put down, we still have the spatial drag map that we showed earlier, and all the little dots are where we had seismometers. And basically, there isn't a really great pattern. We maybe have some more sediment sort of towards the bottom of the array, but basically, everywhere we have like sort of these tens to hundreds of meters of sediment. And so we're still working on figuring out what this means. But so the next step we're going to try and do is basically, can we get out some physical properties about, so what I've just shown is basically trying to map just the sediment thickness. Is there none? Is there a lot? Is there a little? But there's some really, this data is really great. And so hopefully, when we start looking at cross sections like this, we're going to be able to, there's coherence of the wave field. If you're a seismologist, you can maybe see something interesting in here. Like there's these large negative anomalies there, which are coming from the base of the ice sheet. And to get those negative anomalies, you have to have really wet, sort of, I would say like maybe groundwater. You have to have really saturated sediments. So, but anyway, that's where we're at. And we're trying, this is just part of a big project trying to get at what are the physical controls on spatial variability and basal drag beneath the, and there's my timer. All right. Okay.
All right, thanks, Paul. That was great. Up next, we have Shao, who is going to kind of keep us thinking about the ice bed interface here with some mass conservation methods. And Nia is a student, I believe. Is that correct? So please judge. Provide feedback. Yes. All right, take it away.
Oh, this mic. Hello, everyone. My name is Nia. I'm from University of Florida. So this is my first WAIS presentation. Feel free to judge. And I'm going to present about how to quantify uncertainty in the subglacial topography. So subglacial topography buried under 1,000 meters of ice is one critical component in Antarctic ice sheet that can interact with the ice and control other glacial process. But what we know about the subglacial topography is mainly from airborne ice-penetrating radar data. So imagine like you're flying an airplane through the Antarctic ice sheet. It's very likely you will leave a huge data gap in the data set collected. In our study area, the Denman Glacier, it's very visible that the data gap between fly lines ranging between 5 kilometers to 50 kilometers, and we don't know the topography in between. So to generate a complete map used for other purpose, usually inversion or interpolation method are used. One popular bed elevation dataset bed machine use mass conservation equation. So they infer the bed topography from surface velocity by this mass conservation equation. The benefit from that is that the topography inferred is compatible with the observed surface velocity, such that it can be readily incorporated into ice sheet models. However, there are several drawbacks of this method. First one is that they use a parameter to balance between the smoothness of the topography and how much it feeds the radar data. So usually the bed produced will be overly smooth compared to the bed we have observed. And another thing is that they only produce one single map and associated with the arrow map. This arrow map cannot be easily used to represent the uncertainty in topography that is spatially correlated, and it cannot be readily used to propagate uncertainty from bad topography to other glacial process. So other methods do exist, like geostatistic method. The example on the screen, the sequential Gaussian simulation can simulate many topography maps that are possible underneath the glacier. And the benefit is that the simulated maps are realistically rough, and also since we generate multiple topography maps, you can propagate the uncertainty from this ensemble of maps to other glacial process. But they are not necessarily constrained by the mass conservation, which means if you pair this topography with the observed surface velocity, then you are likely to see large value artifact in ice flux, which means it's hard to incorporate into ice flow models. So my question is that, is there any way to combine both of these methods to get some map that is mass conserving, realistically rough, and most importantly, quantifies the uncertainty? So we explore this hypothesis using Markov chain Monte Carlo method. And this basically is a list of topography, each of which only dependent on the one before it. So this list of topography is generated in one iteration. So this shows one iteration. We start with topography A and update that to become A prime. Then we compare A or A prime to decide which one to keep in the next iteration to keep everything simple. Mass conservation can be incorporated into this comparison process, where in this case, we use the residual from mass conservation equation. Basically, we shift every term into one side of equation and see how this topography do not deviate from the requirement of mass conservation. Then we use this acceptance rate to stochastically determine if we accept the updated topography. The geostatistic method, on the other hand, can be incorporated into this update method, where the property of A prime is determined. So in this way, we create a list of topography, and by iteration through iteration, the mass conservation residual is gradually reduced in the list. So we use two different update methods. The first one called weighted random field. First, we select a block in the entire domain and perturb the topography inside the block such that the perturbation is 0 at radar data location. So basically, it just generates a new topography map that is perturbed inside the block, but do not change radar data, so we preserve the radar data. The other method we use is more related with geostatistic. So in this one, we select a block of topography, but in this case, we delete anything in the block that is not radar data. Then the block is resimulated using sequential Gaussian simulation. We use both of these methods in the MCMC chain because they each provide their own benefits. So the weighted random field is good at proposing large-scale feature change on topography, which is necessary to reduce the mass conservation residual. Whereas the one incorporated with SGS is better at preserve the roughness we have observed from radar data. So in this method, we first run WRF chain for hundreds of thousands iterations. At the end of this chain, 10 topography maps are sampled, which are used as 10 initial topography maps to start 10 individual SGS chains. And in the end of those individual SGS chains, 10 topography maps are sampled as a part of the ensemble. Repeating this process for 4 times, we get 40 topography realizations at the end. So finally, it's time to see the result, the main course. And we can see that on the rightmost of the slide, this is the topography generated in our method through MCMC. And it has constructed the diamond trench, similar as bed machine, whereas if we only use the geostatistic method as in the middle, the diamond trench is not there. And if I show the mass conservation residual here, you can see the one using SGS, the thing got shifted on the slide. But hopefully you can still see the color. The mass conservation residual in the geostatically generated topography without mass conservation constraint is 1 magnitude higher than both bed machine and the mass conserving MCMC. And we see actually the mass conserving MCMC generated topography have similar mass conservation residual value as bed machine or even lower. If we enlarge part of the map, on the top, I think it's visually visible that the bed machine is much smoother compared to both the geostatistic and the MCMC. And we can also use a variogram to quantify this roughness, where the higher semi-variance it is on the y-axis, it means the topography is more rough. And bed machine is lower than the radar data and also lower than the ensemble we sampled. Okay, so if we draw a line across this ensemble mean, the cross-section gives us more information about how the topography detail looks like. So in this cross-section, it generally follows the trend of bed machine. But in some location, the ensemble deviates as a whole from bed machine for 1 kilometers. And you can see in a highland area nearby the trench, the variation in the topography, 40 topography realization were produced can reach 1 kilometers. This uncertainty, I don't think it has been represented in the usual bed topography data set we use. And in some critical area nearby the grounding line, like within 20 kilometers of grounding line, the subplot B, we can see in this cross-section there's several hundreds of meters variation by topography. Combined with the realistic roughness we have, that causes the local slope of the bed topography varies across different realization. So the uncertainty there might interact with other glacial process or maybe affect the retreatment of grounding line, but those are the future work to explore further. To give a more complete figure of complete picture about how the ensemble different from bed machine, here is the difference map. And we can see that the ensemble is steeper in the Damien Trench front and has a different geometry at the back of the compared to bed machine. I have some idea of why this is the case, but because of time constraint, so feel free to chat with me afterward. But this difference definitely has exceeded the arrow map provided by bed machine, and also remember that both the topography we generated and bed machine, they have similar mass conservation residual. So what are the conclusions and implications? In this study, we have demonstrated how to use Markov chain to combine geostatistic and mass conservation law to generate topography that is realistically rough, but can be incorporated into ice flow models without the artifacting ice flux. How will this realistic roughness affect ice flow will be interesting to explore in future work. We have also seen the uncertainty in topography that is spatially variable, and this uncertainty should not be presented as one single error map, but should rather be represented as a spatial variability of 2D features. So in the end, I'd like to shout out to my friend also Lamont's work on uncertainty quantification of sub-ice shelf bathymetry, which is presented in the later section. So here's my reference, and yes, that's on my presentation. I would like to acknowledge and thank all the people who has contributed to this work and also helped me through my graduate student journey, and thank you for listening.
All right, thank you, Nia. We're slipping a little bit on time, so we'll save questions for the panel. Up next, we have Jamey Stutz, who will take us to the Rockefeller Mountains and think a little bit about ice sheet history. Awesome.
Yeah, thanks everybody. Really, thanks for having me here, and really great to be here just to keep on time and keep my ADD in check. I'm going to read from my slides. So yeah, today I'll be presenting some work from some postdoctoral work I completed with really big support from the Antarctic Research Center, Teheranga Waka, Victoria University and Wellington, GNS Science, and the New Zealand Antarctic Science Platform. And again, it's just me here today, but I'd really like to acknowledge all my incredible collaborators on this project. So the two aerial photos here on the opening slide are the Rockefeller Mountains in all their glory. Small archipelago of nunataks perched above the outer eastern Ross Sea. These aerial photos come from the first kind of reconnaissance investigations of the area, and serves as really good context for understanding the glacial fluctuations in the area with a huge data gap. So in this talk, I hope to convince you of a really unique historical record told by analyzing archived samples from the mid-'80s, and to provide motivation to return to this area for a more detailed, multidisciplinary investigation of changes since the last glacial maximum. So the Rockefeller Mountains were first discovered by the Bird Antarctic expeditions of the 1930s, and the first geological investigations were undertaken by Seipel and Wade. Thanks to archival footage stitched together by the good folks at OSU Polar Archives and Bird Polar and Climate Research Center, we can see how floats and skis were first used in Antarctica to extend the reach of exploration. As a pilot and a geologist, I think this should encourage us to continue to pursue a shipborne aviation approach to deep field work, but I'll leave that discussion for another time. With a flyby of the Rockefellers, we can see the low relief nature of the nunataks and surrounding ice. You can see there's really a lack of stable platforms for glacial deposits to rest. In fact, there are no glacial deposits here. So in that light, in terms of a glacial reconstruction, this site would seem like a bit of a bust. And that's because traditionally, and this has been primed already for me, so I'm really happy for that, the traditional way to reconstruct a glacier in Antarctica is to run around a mountain near a glacier, collect glacial erratics nicely perched on bedrock, extract cosmogenic nuclides, and determine a precise exposure age up and down the mountain. This is the only plot I'll show is an elevation versus time plot, so those are pretty much the only ones you'll see from me. These dipsticks provide a really powerful way to constrain ice thickness variations through time, and if done up and down a glacier and along many glaciers, we can build an Antarctic-wide chronology of ice sheet change, which essentially we've done. Here's just one example from the Upper Bird Glacier and benchmarked against some model outputs. We argue this provides a really powerful comparison and a good check on some of our models. But without erratics, for this project, we had to get a bit creative and utilize nuclides with a little shorter term memory, in situ radiocarbon, on bedrock surfaces. And so given the lack of terrestrial glacial reconstruction in this region, and since access to Antarctica has kind of always been difficult, and the pandemic and base rebuilds made that even harder, we went to the New Zealand National Petrologic Reference Collection to see what we might find living in basements of various institutions. We were happy to see that a tribe of Kiwi, that's what a group of Kiwis is called, the tribe, igneous petrologists, led by Chris Adams and Steve Weaver, visited the Rockefeller Mountains in the 1980s. We discovered two distinct collections from those expeditions living in the basement of GNS and Canterbury University. And if you're squeamish about using somebody else's samples, you're not alone. I am. Be a suspect. There are many unknowns about these samples, including proper location information, so this was pre-GPS. And most importantly, no idea of shielding, or as Ryan put it, how much the rock sees the sky. And this is a major influence on cosmogenic nuclide production rate. And here just to highlight Claudia's incredible work in the basement of Canterbury University, digging through some of the archives to find these hard-won samples. But after speaking with these guys, Chris and Steve, about their field work and their sampling methods, we discovered that any sample with blue Sharpie labels marked the upper surface that we were interested in. So that was kind of nice. And then also thanks to the observation of desert varnish, this is a really common feature in Antarctic exposed bedrock, we could also determine the weathered face on a rock and assume partial exposure. This gave us some level of confidence in having a subset of samples suitable for our purposes. Admittedly not perfect, but this was 2020 and we were happy with what we could get. So after initially running all 23 samples for the more routine beryllium-10, we discovered a kind of shotgun blast of apparent exposure ages. Even still, these seem quite young for Antarctic bedrock standards. After all, this area is known for being miserably wet and windy, And it's fair to assume that elevated erosion demonstrated by the crumbly rocks found all over the area and tuffoni, erosional features like these discovered by Wade. These data combined with aluminium-26 could classically be used to determine the degree of complex burial and exposure cycles, but not really get us any closer to this more recent emergence of the area. So with this preliminary data in hand, we selected a suite of samples from each nunatak with replicates for some of the larger nunataks for extraction of in situ C14 and a more precise look at the more recent exposure history. So here we can see a bit more focused shotgun blast of ages, all pointing to the late Holocene. And when we compare this with other records for glacial change far away in the Ford Ranges and some radar mapping, layer counting, and Roosevelt Island, we see a really nice overlap in time. This gives us a bit of confidence, and we take these late Holocene ages to represent the emergence of the Rockefeller Mountains, but caution this as a use as a traditional dipstick transect style constraint on thickness. Of course, we have some unknowns here related to sample collection and shielding, but the overwhelming signature is of a very recent exposure. We can add to this study with archive material held at the Polar Rock Repository that come from those early bird field expeditions that we saw earlier, as well as more recent collections from Christine Sidaway with the German Ganovex expeditions, as well as the PolNet team who operated a GPS and seismic station in the area for over a decade. So replicate this study, somebody. Further, these observations, models of retreat and re-advance timings by Sarah Newhouse and colleagues and Dan Lowry and colleagues also point to a late Holocene retreat along the Ben Shadler ice stream and suggest a potential re-advance in the latest Holocene. So we think we have a real signature here of the initial emergence, and one of the remaining questions for me is there a re-advance signature here at the Rockefeller Mountains? Namely, was the ice sheet smaller at some point in the Holocene, and is this reflected in subglacial surface exposure data? So here's where I make the case to return to the Rockefeller Mountains for subglacial drilling right off the flanks of an optimal position, probably lower elevation and looking right at the eastern Ross Ice Shelf. And while we're there, we could collect a solid transect of bedrock samples for a tighter constraint on the work I've presented today. And finally, and I'm happy this has also been primed for me as well, we could collect a pile of snow petrel puke. Stick with me here. We have a permit to collect this already. So the Rockefeller Mountains are home to a gallon of petrels. That's the name for a group of petrels. Possibly one of the largest in Antarctica with an estimated 20,000 breeding pairs. These amazing birds feed out to sea and live in rocky nests on nunataks. When they feed their young, like most birds, they make a big mess. This pile of puke has been given a really sophisticated name, as we've heard, called Mumio, and contains an amazing chronology of petrel occupation with the bonus of containing a bunch of lovely clues to diet, oceanographic conditions, and can most likely be tied to the ice core at the nearby Roosevelt Island. And like ice, it needs to stay frozen. Also, the place is covered in lichens, mosses, and fungi. So that's my pitch for taking another trip out to the Rockefeller Mountains. Unfortunately, this will be, or fortunately for maybe somebody in the crowd, this is going to be somebody else's project. Closing down my Antarctic research chapter and taking my skills and interests to studying the Laurentide ice sheet with the Great Lakes Coalition, Great Lakes Mapping Coalition. This is not a goodbye, but it is a see you later. I'll remain passionate about Antarctic science, and just like to take the opportunity to thank NASA and NSF for travel funds, to come to WAIS, to hang out with you guys, this community as a whole, the massive support I've received over the last 15 years in my Antarctic career. And we've just finished an amazing field season along the Bird Fjord where we found a radix perched a kilometer above the Bird Glacier. So I'm really excited to see what story Lottie Stevenson and other at Vic will tell us about this mighty glacier. You can follow me along at icetime.rocks for silly field stories, but as I get pulled off the stage, I'll be spending a lot more time with these two. So thanks for your time.
All right, thank you, Jamey. One more talk in this session. if I can escape this. Julia is going to close the session. Julia Andreasen is also a student, so please provide feedback. Yeah, she's going to talk to us about coastal ice rises and some reanalysis work that she's been doing there.
Hello again. Thank you for hanging in there. We're on the last day, final stretch. Hi everyone, my name is Julia Andreasen. I'm a PhD student at the University of Minnesota, and today I'll be talking to you all about our reanalysis evaluation of climatic controls at coastal WAIS ice rises. So to begin, why do we care about the WAIS and what's so unique about its coast? WAIS is dynamic, and it's a critical region of Antarctica where ice, ocean, and atmosphere converge to drive change. And this change is where Antarctica experiences its greatest atmospheric climate variability, as well as its persistent and accelerating mass loss, which has caused major concern for irreversible retreat, as well as sea level rise contribution. So there are many factors that contribute to this region's climate variability, and this list of main forcings is not exhaustive, but I'll highlight a few that will come up in this talk again. So first, the Southern Annular Mode, or SAM, describes the position and intensity of the westerly winds that circulate around Antarctica. And currently, SAM is in a positive phase and trending more so, which results in a strengthening of the winds along WAIS. Next, we have the Amundsen Sea Low, or ASL, which is a quasi-stationary center of low pressure along the WAIS Pacific coast. And during El Nino events, higher ASL air pressure typically drives northwest to southeast near surface winds, which transports warm, moist air from the ocean to WAIS. And this both increases snow accumulation on the surface, as well as stimulates this circumpolar deep water upwelling that melts ice shelves from below. So what's the best way to directly observe all of these processes and extend observations back in time before the satellite era? Well, another key aspect about coastal WAIS is the existence of ice rises along the continent's periphery and embedded within ice shelves. So WAIS ice rises are prime locations for reconstructing coastal Antarctic climate history. These small but grounded and elevated features form from localized snow accumulation on shallow bedrock and preserve high-resolution records of past climate. So these ice rises essentially act as natural archives, with snow accumulating on the windward slopes due to patterns like katabatic winds from inland Antarctica and cyclonic storms from the Southern Ocean. So structurally, ice flow extends from a central divide where there's minimal distortion beneath that divide, which really allows us to preserve snow layers below that divide, as you can see in this Operation Icebridge radargram of Martin Peninsula. And because of this, ice cores that are extracted from ice rises are super ideal and reveal detailed records of temperature, precipitation, and atmospheric conditions over time. So there's a growing number of ice core projects that have taken place on ice rises, and with each location here is represented by red dots on this map. And there are clear regional gaps in ice core locations along the coast, specifically along the WAIS coast. So extracting more ice cores along our region would help capture glacial and interglacial climate changes, as well as reveal interactions with grounding zone dynamics. I'm just gonna put a star right here because this is an important one. So taking these previous projects as motivation, we'll now explore WAIS climatology through 13 ice rises along the coast that we've split into the west sector and the east sector. The analysis of these ice rises will help answer key questions about the region, such as how can snow accumulation at coastal ice rises be used to reconstruct Amundsen Sea regional climate forcing, as well as what can ice rises reveal about climate forcing at surrounding ice shelves, specifically ice shelves that are super vulnerable, like Thwaites and Pine Island Glacier. So through these questions, we'll also determine which ice rises are ideal for future ice cores. So in the 2023-2024 field season, I was lucky enough to participate in the RICA project, which collected 2 150-meter cores from Canisteo Peninsula, which was that starred ice rise. And Peter Neff will share more about that in the next session. It's also important to note that there have been other cores collected along the West Coast, including Sherman Island, Sipel Dome, and Roosevelt Island. But this is only the beginning of what is possible in terms of ice cores. So before being able to take more ice cores, we dive into the reanalysis data sets that we have of these locations. And my work does cover ERA 5, MERA 2, and RACMO, but just for the sake of this presentation, we're only going to cover ERA 5. So looking at the annual temperature and precipitation variables and trends for each individual ice rise, as well as the overall sector, we first confirmed our very basic understanding that warm years are wet years and cold years are dry years. Nothing super surprising there. We then looked at the seasonal patterns for temperature and precipitation. There's an accumulation dipole that we saw earlier, where warmer and wetter average conditions existed in the west sector, while the east sector ice rises experienced cooler and drier conditions. And these regional differences really suggest that certain areas are better suited for capturing seasonal extremes, which helps guide us in selecting those ice core sites. So to better understand how atmospheric conditions shape snow accumulation at coastal waste sites, we isolate precipitation rates, assuming that precipitation is snow accumulation at each ice rise, and calculate how they correlate with key variables within a defined region, like here, the Amundsen Sea. Looking specifically at correlations with westerly winds or zonal winds, we observe a clear west to east gradient, so west being those reddish dots and then east being more blue. So in the west sector, Roosevelt Island and Guest Peninsula and Dean Island exhibit this really broad and strong correlation with westerly winds. That's why their circles are bigger. And this suggests that strong winds tend to reduce precipitation in this region due to the negative correlation. On the other hand, Farwell Island, Nova Peninsula, and others in the east sector show little, if any, correlation to broad westerly winds, which is why they are small dots. Similarly, we look at the correlation between ice rise precipitation and global meridional winds, or Z-wind. So Z-wind is different from U-wind because it describes a north-south airflow and can drive significant moisture transport from the open ocean or across the continent onto the West Coast. So we can see that really any ice rise here can have a strong correlation with the V-winds that are located north of it, and anti-correlations to the far eastern areas of blocking high pressure. So in other words, any ice rise will reconstruct meridional winds from its north and east. But in a reanalysis space, you can also define the box however you want. So we're gonna change this bounding box and use a smaller one defined by the often cited Steig et al. 2012 to represent the continental shelf break region. Our correlation plots start to look really different. For zonal winds, we don't really see much of a consistent correlation, but for meridional winds we do. And particularly, it shows that ice rises that are closest to that box have the strongest correlation. And this is just a reiteration of all of that. And then we also analyzed how precipitation correlates with sea surface temperature and sea ice, revealing another west to east correlation or gradient. So in the west sector, ice rises show some strong positive correlation with sea surface temperature, indicating that warmer ocean surfaces boost snowfall, which is likely due to Pacific moisture transported from the Amundsen Sea low. And then in the east sector, we see sea surface temperature correlations are weaker, which suggests less of a direct influence from ocean warmth. And then with sea ice, we see kind of the opposite thing. So sea ice is the blue, sea surface temperature was the red. And we see the west sector has strong negative correlations with precipitation. So as the sea ice decreases, this open water supports more heat and moisture transport, which, thanks to Sam and Enso, allows for more precipitation. So lastly, we'd like to further illustrate these climate details and dynamics through geopotential heights. And so it's pretty consistent in our different geopotential height patterns here, but we have a pretty strong positive correlation in the west sector for Roosevelt, Dean, Guest, and this typically reflects that more snowfall occurs when Z500 or any of these are higher. So this means that high pressure systems or atmospheric walking events that direct moisture towards these sites increases the precipitation. So then that's another little summary, and we'll just jump to our conclusions. So I've covered most of this, but one thing I want to also say is that middle of our coast sort of reconstructions, so ice rises that are near Thwaites, are also really super important, because although they don't capture that coastal extreme, they do capture really important ice shelves like Thwaites and Pine Island Glacier. And then this is just a final little video of penguins. Thank you.
All right, could we get all the speakers from this session to come back up for the panel? We have, I think, about 30 minutes to discuss the talks here. And Marion, if you want to, okay. Okay, Julia's got it, cool. Remember that they started with the early career review, so if you have questions on that, feel free to ask those of Julia as well. Are you watching online, Matt? That's fair, but do you want me to watch online is my question. Go ahead if you have.
Hello, that was awesome. So this corner of Ross Ice Shelf seems really interesting, particularly when you combine what you showed, Jamey, with what Roger was talking about. So Roger showed, mid-Holocene retreat is not atmosphere. I think because that corner is where warm water gets into Ross Ice Shelf, if it gets in, you showed it thins later than deeper into the ice shelf, so it's probably not the ocean driving this. So we're truly looking at an ice dynamic signal 8,000 years ago, which is really cool. And then Julia showed that this is kind of a variability signal that we could get. So I'm wondering what else there is to do right there. Like, what's the next set of stuff we need to do to really figure out how, when, if signals we see are signals of warm water getting in to the Ross cavity, which is the biggest uncertainty according to Helen Cerruti, and how to untangle some of these processes that might happen. Did that make sense?
Yeah, thanks for that question. Yeah, I think there's a lot to do there, obviously. I'd love to see a ship parked off the Edward the Seventh Peninsula there, and maybe doing some yo-yo casts with the CTD to get a look at that warmer water, dropping some cores to get a good idea of the paleo constraints out there, which we don't have. The Kiwis have, as part of the Antarctic Science Platform, have or at least still earmarked to go to Rockefeller Mountains and Roosevelt Island for some active source geophysics. So there is some attempt, and probably within the next 5 to 10 years, of getting back out there. This was kind of on the list for us pre-pandemic, and forced to be a little closer to the mountains there. So yeah, I think the Rockefellers themselves have some attraction, but I think the the nearby ocean, seafloor, and yeah, maybe some sub-ice shelf stuff as well.
Yeah, I think my answer is pretty simple. Ice cores are always needed. So anything, I mean, Gust Peninsula would be really great. I mean, we have one from Roosevelt, but I think anything that would show us, sort of capture that climate history anywhere beyond what we have now would be excellent.
I can keep asking questions, but please, someone else do this. Paul, your talk was phenomenal, and I can't wait to see the rest of the ITGC active source work. But I was pretty surprised that basically you're showing Thwaites scraped everything away. There was not much sediment there, and so it's the hard rock that really matters for the dynamics.
I think it's I think Byron Perizak and his group, right, have shown this really well, right? It's the space, where it's not only is there dirt or not or sediment, but that spatial variability. And if Louise was here, she would show up glacier, we have hundreds of meters of sediment. So I think what we're really getting, and a lot of the radar work, that Canute and Nick were involved in, is that, there are these bedrock crag and tail features, and it's a really heterogeneous subglacial landscape as far as bed type. And I think a lot of the modeling work is going to show that that's really important. And I think we just need to be creative, like whether it's geostatistical methods, how do we sort of capture that? Because we can't measure everything, but I think how we intelligently take what we do know and, yeah, so it's definitely maybe there are places with less and more sediment. And that's, yeah.
Were you surprised at the sediment thicknesses you were finding? Or was that what you thought you would get?
I don't think we had any idea, right?
Okay.
It's really below sea level, right? I mean, you go places in the, the Saipol coast, and you have tons and tons of sediment, and definitely looks like places like in Leo's work where it's been scraped off, and other places where it hasn't. Or there was the nice poster yesterday where we see places where we have, million-year-old sediments right next to places where it's been excavated.
I can perhaps add a little bit to that from the perspective offshore, from IODP 379, who drilled offshore in Amundsen, and the Pliocene was a massive sediment factory during the glacials. A huge volume was being flushed out. Every glacial, just massive thicknesses of silts that were coming in off the continental shelf. And the Pleistocene, that sediment machine shut down. And so the amount that was being produced from glacial advances was tremendously reduced. So clearly those channels had been carved earlier, and what sediments left there is greatly diminished over what it had been previously.
Great talk, everyone. I have a question for Paul. So I saw the seismometer, like the system of those seismometers, and I'm just curious, how do they communicate with the recording station? Is it like you have to deploy them, and then maybe after some time you go back to grab the data, or is it like a real-time logging where you have your recording station somewhere reading the data?
Yeah, it's a very great question. This is one of the things as the sort of geophysical infrastructure community we're really struggling with is, so these particular instruments, yeah, we left them out for, I don't think I made that clear yet. So these were out for about a few weeks each. And so there's oftentimes we would like to leave out seismometers in Antarctica for years at a time. And right now, current struggle is getting that data back remotely is a pinch point. We haven't, because the data volumes are so high. You basically have this problem that if you want to get the data back without going to visit the station, you need to take out so many batteries to power the communication system. It becomes problematic, but this is so we usually almost always now have to go, and unless it's at a permanent station, we have to go grab hard drive, basically.
Oh, okay. And also, I saw like one of those data collected, and it was so clean. So I wonder if there is a pre-step where you configure the recording system so that you have a range of frequency that you can remove as like artificial noise or undesirable data, and then you just record the specific one that you showed.
Yeah, so I definitely skipped over that. So there's definitely a lot of, there's definitely some conditioning of the data before we get to the point where we can interpret it for subglacial structure. Yeah, thought we could talk for
Thank you.
a long time about that.
Thank you.
I might just jump in real quick with an online question, if that's okay. So this is a question for Jamey from Joe Johnson online. It says, great talk, loved it. I maybe missed it, but how did you deal with the lack of shielding data on your archive at Rockefeller Mountains?
Yeah, thanks, Joe, and thanks for the recent email as well. I just, should just email me after my talk. So Joe's great. Yeah, it's a big unknown. Yeah, just admittedly, kind of blasted right through that, and for all cosmonauts in town here, it's really uneasy, to do that, to accept that you don't have shielding. I think there's a real good opportunity, particularly with samples held in other repositories, as well as the samples we didn't run, to really up the numbers game here, and not necessarily look at this site as a true transect, but just as a pilot study. We were lucky with the blue Sharpie thing, and the fact that the Rockefeller Mountains really, the shielding is going to be self-shielding. There aren't mountains around that really get in the way. So there's quite a few assumptions there. It's uneasy, but we take a risk, and what we saw, I think, was pretty compelling. So to me, this drives more motivation for to basically run as many samples as we can for this. And it'll be a long time before we get there, so we got some time, hey? Thanks.
My question is for Naya. That was an incredible talk. I can't believe it's possible, and congratulations. When you impose the mass conservation, I guess you have to assume something about basal sliding. And so, like when you go from somewhere where the bed is frozen to it goes over a lake or something and it slides and it's more plug flow, and then it goes over an area where it's not sliding again, that has some expression in the surface. So I guess, like, how does that show up in your mass conservation?
So it's a question like how the different like subglacial features could affect the mass conservation.
Yeah.
Is that?
Yeah, and does your mass conservation assume it's all sliding, none of it's sliding, it's all sliding in the same way?
Yes. So I think the mass conservation we use pretty much assume the ice surface velocity can approximate the depth average velocity.
Gotcha.
Which means the ice just like idealistically moves through the topography, and yeah, I think because we also constrain the region where we use the method to high velocity area, so I think it's sliding dominated location. The same assumption is used for many other topographic inversion. That's why I also use that in this work. I think it would be interesting to see if other features could be incorporated, but it's like where those features are on the bed topography is also a question. So the current method we use basically assume the ice surface velocity is the depth average velocity.
Awesome. Thank you.
Thank you.
This is a question for Paul. Really nice talk. I wondered if your methods can get at basal thermal state at all, and if so, if you could comment on that for the area you're looking at.
Right. I mean, so that's, I think one of the things, and especially some of the more active source seismic measurements, like Olaf Eisen's group is doing with the Vibrosize, and Alex and Sridhar, and other people are doing with the sort of explosive source seismic. I mean, getting at that, really that interface, I still think measuring the shear wave speed of sediments is really still like one of the best ways, because basically what you're getting at then is the water content of the sediment, if there's sediment. And I still think that is kind of one of the best ways, if you know, because that's an indirect indication of something about the thermal state, because you have water saturated sediments. Maybe not thermal, but you have water. So I mean, and Leo Peters had a paper, trying to get at in glacial temperature with seismic attenuation, but I don't think much has been progressed in that. But I think, I think so maybe not. Yeah, I don't think seismic is the way I would go to get at thermal state, but definitely is there water, and how much water is there? I think and essentially what is the porosity, effective pressure of these sediments? I think is what seismology is particularly good at. Yeah. But I would talk to radar people about thermal structure.
I have a question for Jamey, kind of going off of what Joe asked online. You mentioned there's pretty high erosion potentially at this site, and so I'm wondering if you can kind of try to contextualize some of the very young ages in terms of a assumed erosion rate, and also mention what production rate you're using, specifically for the for the carbon-14 ages.
Yeah, thanks for that. And this really highlights that we're kind of on a bleeding edge of this. So to your first point about erosion rate, I think on this scale, so the erosion rate at the Rockefeller Mountains is probably high for Antarctic standards. I think on this time scale, regardless of what that erosion rate is, it's still negligible. For the older, potential complex burial exposure cycles, probably quite important, and that's where the beryllium aluminum pairs could be really helpful. To your second part, I'm just using the Balculator, so the 2008 Cosmo, which has issues with dealing with muon production, and a really big open question here. So the potential here is that some of these ages could shift in the older, younger direction. So this is a huge element of this, beyond the kind of in-field sampling methods and all that stuff. So when you guys figure out muons, let's talk, because I'm really, that's way outside of my expertise, and I know this is a really open area of research. So yeah, thanks for the question. If I could just add one more thing to the thermal bit, and a creative use of rocks and erratics in this case. Rocks can be hotter than others, and so the radiogenic component of particularly granites can be used to constrain that radiogenic component of the geothermal heat flux. And so I just implore all of you to kind of dig into some of that research and use those erratics to talk about the upstream geothermal heat flux in your favorite glacier.
Hi, great talks, everyone. Whoops. I guess my question is more for Julia. I really liked the approach that you're using to sort of understand the modern processes that might be driving ice accumulation, or, and I guess this ties in a bit with Jamey's work too, like what are the sort of processes that are leading to sort of thinning. And so my knowledge isn't great on this, but like, are we doing this in other regions of Antarctica as well? I guess like from the paleoceanography perspective, like we're always trying to compare our records to like the Southern Annular Mode or INSO variability. So yeah, I'm really excited by your work, and I think like we can do a lot more in other regions to sort of better understand like the long-term records too, and like what's driving changes. So do you know like if we're thinking about doing this in other regions as well?
Well, I think, so we have really focused on WAIS because we know the importance of it and its vulnerability, but I know that up in the East Antarctic ice sheet on the coast, sort of in the upper Marie Birdland area, they are taking a lot of ice cores from ice rises up there, and I think that's sort of been our motivation to understanding, how we can correlate reanalysis data sets with ice cores and then also with Operation Icebridge radar-grams, so sort of having all three of those different things, two of them a bit more modeled than the ice core, obviously, but if those data sets can sort of confirm each other, then we'll have a better sense of, one point, but if we can do an array, then you have more of a spatial instead of just temporal understanding. And so I think for us, that's what we know that we're trying to do here, and I think that's been happening in other areas as well. That kind of answers your question, but I'm excited about your excitement.
Yeah, thanks.
I'm going to follow up on Dusty's questions, Nia, because your talk was fantastic. Have you played around with scaling that surface velocity to represent a more frozen at the bed case all the way through full sliding case? Like, is that in that uncertainty that you're showing at all, or are you just plowing through with sliding? Because that can tell us a lot, right? Which of these, that gives you a full process uncertainty, but also can tell you something about how much we're sliding or not.
Yeah, thanks for the question. So I was also thinking about that after this next question. And so currently the uncertainty do not incorporate that uncertainty. It sounds weird, but it's possible to do, I'm thinking about if use function that incorporate the surface velocity, which the output of function is the so-called depth average velocity. If the function variability is constrained within a certain distribution, then maybe the result of this function could tell us something about whether the bed is frozen here, etc. But another thing that I think worth to be considered is the uncertainty interplay between the modeling. I guess this one is modeling uncertainty, and also the bedrock uncertainty. They can compensate each other. So it's necessary to generate pairs of how much the bed is frozen and how the topography will look like in pairs. It's more I guess it's joint inversion or some sort of things like that. So yeah, so to answer your question, currently the uncertainty of how the surface velocity represents the depth average is not represented in the uncertainty I showed, but that could be something to incorporate into this workflow. Thank you.
I'm going to ask a harder question now, though.
Yeah.
I mean, you'll see this comment because I put it on the form, so I'll say it publicly. You made a great case that we have solved bed topography, right? This combination of the statistics and the flow modeling to get a bed is incredible. How much more radar mapping do we need?
Yeah, actually, I think that's, so once we have the topography uncertainty under the current radar, maybe that could be used to inform where future radar location is valuable to add into this constraint, this ensemble to constrain the topography further. How many more, of course, the more the better, but also need to consider the price of actually sampling the radar in the region. And even with really detailed sampling, because radar is collecting the bed topography along the flat line, that's what I think. So in the end, there's still some variability in the topography if you do sparse sampling. It's just how much this variability is. And I do think having the current data and estimate uncertainty from the current data can help to inform where we could know the bed elevation to reduce this uncertainty.
I'm going to keep asking this question every time you present until it's we don't need any more flights, we're good. We just need repeats.
Thank you.
Thank you so much. A question for Nia. Thanks again for your great talk. I really enjoyed it. And I am Massimiliano from Italy. And I was thinking, have you ever thought about the possibility to run co-kriging sequential simulations for constraining the bedrock topography to the surface one? Because you can see it, maybe.
Yeah,
would be a good option. Thanks.
The co-simulation or co-kriging?
Yeah, exactly.
Yeah, I think similar work has been done in my advisor Miki's work, and that has been similar things has been done in geostatistic simulation before. But I guess one of the potential difference could be the method I'm currently using. They use small variation in bed topography to conserve mass. So instead of adding the small variation on already mass conserving topography, it's using the variation to make the topography mass conserving. That could be a potential difference. But yeah.
Thank you so much.
Thank you.
So I'll ask a follow-on to Matt's question. If you were going from scratch, if no radar data existed, but you understood this, how would you design your surveys? What does the technique want? Are you trying to just find province boundaries? Are you surveying super detailed to get statistics? Go to the next one. Is it rings? What is the ideal shape? This is pure enthusiasm, not
I guess I already failed the exam after 5 seconds of silence. Ideal shape. I think that'd be an interesting question to ask. So detailed geostatistic properties would definitely be very helpful to know the roughness of the bed, but also how this geostatistic varies across the spatial would be interesting. So currently the bed we use a single roughness to constrain the entire domain, but in realistic situation this roughness could also change. So maybe in the future work, certain area, which area have what roughness could be an important factor to see, okay, so we're gonna simulate really rough bed here, but a little bit more smoother bed there. The shape of I guess both how the radar has sampled the bed has sampled the spatially distributed bed, and how would, I guess both point really localized sampling and the widespread sampling combined together would be ideal. But also, I guess it's too pricey. But thank you for the question.
No, thank you.
I have a question for Paul, if no one has other questions. Is there what kind of prior properties you could use to kind of determine where you're going to put on this the passive seismic arrays, such that maybe this part is important to know the sediment thickness?
Yeah, good question. And I think you've passed your comprehensive exam, by the way. I think that was totally, and that was really fun hearing the conversation. I think we definitely, where we planned our geophysical surveys, I could have spent 10 minutes just showing all the lines and everything. It was definitely based on the inversions of flow speed for basal friction. That definitely helped guide where we think bed properties might be more important. So I think that's the thing, is I think as a ground-based geophysicist where we have limited logistical resources, having access to the kind of products you're producing really help us guide where we need more data. So I think there's this, because we can't sample everything. And then I think what's maybe exciting about these passive methods, which is not what this array was designed for, is it does give you kind of a very, it's relatively cheap compared to a lot of the active source geophysical methods, both in time. And so it kind of, moving forward now that we have these new technologies, because we couldn't have done this kind of experiment 10 years ago, is you could even design very quickly, doing a broad survey and then figuring out where is interesting, right? There are like, even here there are places where it's like, oh, there's no sediment here, there's some sediment here, and you start to get zoning in where you need to go do your active source. You know, where is it that you have crag and tail features or megascale lineations and things like that, you know? I think, I'm not sure if that answered the question. Yeah.
I had another question for Paul. You were looking at sort of far field earthquakes, but I'm curious if you can comment on near field seismic sources indicating if there's a change in bed sliding in these regions.
Yeah, I mean, and that's totally the reason this array was put out. I mean, we weren't thinking about doing this at all when we planned or collected it. And so that's what really is going to be Jaden's PhD at the University of Madison is, and there's just, I mean, he had a movie at the ITGC where he was showing ice quakes in real time, like not even like sped up, just like every second there are these like little earthquakes, you know, right? Ice quakes coming from these magnitudes. If you don't know, there are these like little magnitude -1 zeros, basically little earthquakes coming as the ice is sliding over the bed. And he's going to have amazing maps that are going to basically map out variations in basal friction along this, you know, 20-kilometer array that we've never been able to do before, and it's going to be amazing. And hopefully, yeah, so we can start to get at things like what are variations in effective normal pressure, maybe, and friction, and yeah, it should be exciting in the next 2 years. Yeah.
Awesome. Excited to keep an eye out for that. Thank you.
Yeah, yeah.
Well, we have just a couple minutes left, so if there's one more question, then someone could ask, but if not, then perhaps we could give them another round of applause.